It was January 1978 when the Pentagon received a call from the Soviet High Command. The Soviets would never do something that could willingly reveal one of their closely held secrets, but this was an emergency of unprecedented scale. One of their state-of-the-art nuclear-powered satellites, designed to spy on the Americans, was quickly veering out of orbit. Worse yet, the security system that ejected the nuclear reactor in case of malfunction had failed. The satellite was coming down with an active reactor on board. The satellite would likely fall on the North American continent. The storm of radiation it would unleash would be a blight, so much so that the Soviets feared it might trigger World War III. As the Cold War escalated, the Soviet Union faced a critical weakness. They could not match American naval supremacy. The West's nuclear-armed carrier strike groups roamed the seas, untouchable, and without real-time tracking capabilities, the USSR was falling behind. They needed a solution that could work in any weather. Conventional spy satellites were useless. Clouds obscured their view. They could use a synthetic aperture radar, SAR, capable of piercing through darkness and storms using highly specialized radar technology. There was just one problem. SAR required enormous amounts of power, far beyond what contemporary solar panels could generate without making the satellite too heavy to maintain orbit. Soviet engineers devised an unthinkable solution: a nuclear-powered satellite. The Soviets embraced a solution even the Americans had deemed too dangerous: the BES-5 Book fast fission reactor. This orbital power plant was a masterpiece of miniaturization and a nightmare of compromised safety. Without the moderator unit of conventional reactors, it weighed just 385 kilograms but sacrificed critical safety features. At its heart lay 31 to 44 kilograms of uranium-235, enriched to a weapons-grade 90%. 6 control rods and beryllium reflectors trapped neutrons in its core, driving a reaction that generated 100 kilowatts of thermal power. Through a liquid sodium-potassium system, this beast converted its nuclear fury into 3 kilowatts of electricity, enough to power the radar but at a terrible price. Unlike conventional satellites, which harmlessly disintegrated upon re-entry, a RORSat failure could mean a nuclear catastrophe. The Soviets, aware of the danger, developed a fail-safe mechanism. When the mission was complete, the reactor would detach and boost itself into a high graveyard orbit, ensuring it never fell back to Earth. At least that was the theory. What if the fail-safe failed? What if a satellite lost control? Each RORSat launch sent a nuclear time bomb into space. The Soviet RORSat program consisted of 33 reconnaissance satellites. At least 5 of them failed. The worst case? Cosmos 954. On September 8, 1977, Cosmos 954 rode a Cyclone 2 rocket into space, lifting off from Baikonur at 1:55 p.m. It circled Earth every 90 minutes, working as intended, until December. That's when things went wrong. The orbit destabilized. The satellite began to drift off course, slowly. More concerning was the fact that Soviet officials were unable to trigger the fail-safe mechanism. The reactor was stuck. It couldn't be ejected into a higher orbit. The Soviets knew they had lost control. To their credit, they warned the US. They admitted that the satellite was beyond any Soviet measures and that its onboard nuclear reactor was still intact. The whole 4,000-kilogram machine was coming down. No one knew exactly where. Despite being a ticking bomb in orbit, it would take months to fall. Early estimates placed re-entry in mid-1978. They were wrong. On January 24th, the satellite entered Earth's atmosphere, tearing through the sky over northeastern Canada. The Soviets insisted it had burned up. They were wrong. Again. The Soviet satellite blazed across 600 kilometers of Canadian wilderness, burning through the sky for 3 minutes before vanishing beneath the Arctic snow. Operation Morning Light launched immediately, a joint US-Canadian mission with an open secret. While officially tasked with containing radiation, American teams from Nevada hungered for something more, their first glimpse of cutting-edge Soviet technology. The search zone, initially split into 8 sections and later 14, saw its first explorers, a 22-man Canadian radiation team. They were assigned what was probably the most critical task: to assess how radioactive the area was and how dangerous the remains of the reactor were. But even the land itself was treacherous. Endless tundra in all directions, with no real landmarks to guide them. As they thrust deeper into the frozen wasteland, two US C-414 aircraft flew in with radiation scanners bolted onto Canadian planes. At 4 a.m., 4 search planes were airborne, sweeping over 500 miles. First, they checked population centers and main roads in case radioactive fragments had landed near civilians. Computer models tracked the satellite's fall, guiding the search teams. Then, at 10 a.m. on January 26th, one of the planes detected radiation near Great Slave Lake, the first solid lead. By January 28th, warnings went up. Signs in English and multiple indigenous languages told locals what had happened and what to avoid. Despite the massive and unprecedented operation, one of the first finds would be made by a completely unexpected group of people. 2 men, part of a 6-man team on a 15-month dog sled expedition across the Northern Territories, pushed forward through the Warden Grove wilderness. Suddenly, they saw something that did not belong in the frozen landscape they were so accustomed to. Something unnatural, twisted metal, half buried in the snow. It looked like wreckage. Maybe a crashed plane. They had no idea. Later that day, as they returned to camp, they heard the news on the radio. The Soviet satellite had crashed. Officials suspected it had touched down in that very region. They contacted the authorities. Within hours, a recovery team was on its way. When investigators arrived, their instruments told them everything they needed to know. The chunk of metal, later dubbed the antler due to its long, twisted appearance, was still pulsing with radiation, 15 Röntgen per hour. The men had stumbled onto something dangerous, and it wasn't the only piece out there. By January 31st, helicopters began delivering ground crews into the desolate, frozen expanse of northern Canada. Armed with radiation scanners, search teams moved methodically, scouring the tundra for wreckage. Some of the debris was immediately flown to Yellowknife, others to Edmonton, where scientists could study them under controlled conditions. The search stretched across months, unfolding in 2 phases, from January to April, then again from April to October. As time passed, U.S. personnel gradually stepped back. They were not very interested in cleanup duty. They wanted to investigate the reactor. The fragments told their own story. A large metal drum, later nicknamed the stovepipe, was found in Sector 1, intact but cold, free of radiation. In other areas, searchers uncovered steel plate shards, some still giving off 15 Röntgen per hour. Over 40 beryllium fragments littered the ice in sectors 10, 11, and 2, some emitting a terrifying 100 Röntgen per hour on contact. Had the material fallen in a population center, the devastation would have been indescribable. A Chernobyl-scale crisis, years before the Ukrainian disaster took place. Had it fallen on an American city, the whole ordeal might have finally escalated the Cold War into World War III. Fortunately, the radioactive material was far from cities and large towns, and the recovery crews worked tirelessly to remove as many pieces as possible to prevent the radiation from affecting the wilderness. Small chunks were scattered everywhere, the highest among them pulsing with radiation between 10 and 30 Röntgen per hour. And then there was the most dangerous kind, a single fragment, its jagged edges emitting a staggering 500 Röntgen per hour, more than enough to take a person's life. In total, nearly 4,000 pieces of debris were recovered. The worst of them had to be locked away in shielded containers, while lower-risk fragments were wrapped in plastic and removed from the site. The scale of contamination was frightening. 2,500 curies of radiation, nearly a fifth of the satellite's entire nuclear payload, were recovered. By 1978, Operation Morning Light had reached its end. The pieces of the wreckage had been found. The radiation was contained, but one final question had not yet been answered. Who was going to pay for the expensive ordeal? According to the 1972 Space Liability Convention, the answer was clear. If you put something into orbit, you're responsible for the damage when it comes crashing down. Canada sent the bill to the USSR, $6 million. The Soviets ended up paying just half that amount. Even after all the radiation and all the risks, the USSR didn't stop. The Roarsat program continued for another decade. They kept launching satellites like the one that fell apart in Canada. It wasn't until 1988, 11 years after the crash, that they finally stopped.